So how do we assign these keys? We will look more into that in the presentation in the second half of the class, but there is a certification authority that we need to go to that will certify that we are who we say we are. And we have to present some identification documents to them and say, we are Google, or we are Apple, or we are something else. And once we prove that, this trusted third-party certification authority will issue a pair of keys to that company or to that organization or to that person. It will issue a public and a private key pair and a digital signature for them to use in a certificate. So it's going to give them a certificate with all these keys and signature in there. And so when they have that, they can publish that public key. And anybody who wants to talk to them would use the public key to encrypt, apply the encryption method, encrypt the message or the communication and send it through the network. And then the only person or company that can decrypt that message is the one that has the private key matching. And so, remember, it's a pair of public and private key. The public is published on the website. Anybody can take it, encrypt messages, but the only person that can decrypt it is the one that has the private key. Now, if we want to use a symmetric key, we can do that. And that's what usually happens when we have secure connections. So when you log into the bank account and it says, you are using a secure connection, that's when we're using the secure socket layer. That's when you will see in the browser says HTTPS secure protocol. With that secure socket layer, first we would use the public and private key to establish sort of a connection between the sender and the receiver, and once this connection is established, we would exchange a shared symmetric key, and that symmetric key will be used for the rest of the communication. In other words, the key will be the same, but they need some way to exchange it securely. With the secure sockets layer, that's what's happening, and the reason that's happening is because it's much faster and easier to use the same key than to use different keys. When you use different public and private key instead of symmetric key, then it adds more overhead and slower. So they just use it in the beginning to establish the connection and then pick up some random number and use that same number for the rest of the communication. So this is an example of a symmetric key encryption. It's called a substitution cipher. It's one of the oldest methods that existed. And it was actually used in the war. It was used in the World War. So the Germans used this method to encrypt messages during the war. So they have created a special machine that did exactly this, replaced one letter with another letter, and this way their messages were unreadable. And the Americans tried to guess what was the key for that and deciphered some of the messages. So they were getting advantage for some time until the Germans decided to change the code. And then the Americans lost a lot of soldiers and ships during that time. So how does this work? They will substitute, it's called monoalphabetic substitution because it substitutes one letter with another letter. So A goes into Q, for example. B goes into W. C goes into E. And so on. In order to decrypt the message, we need to know the key. The cryptanalyst knows the general algorithm or the encryption methods. So cryptanalyst is the person that's trying to crack the encryption. They know the method, so the encryption method is public. We're replacing one letter with another letter. The only thing they don't know is the key. In other words, the key is a sequence of 26 letters in English language in this case. Is it easy to guess this key? How many such keys do we have? How many combinations of 26 letters do we have? Length is 26 letters. 26 factorial. That's a big number, right? That's a lot of combinations. If we were to, start trying every single one of these, even with today's computer hardware, it might take a long time to try all of these. So this is not the weakness of the algorithm. This is the strength of the algorithm. How can this be broken?
Guessing every single possible one, what makes sense.
That's a brute force. That's a brute force attack.
So
That's gonna take.
how do they exchange the key actually?
They did not have computers back then. They were doing this manually. People were doing it manually on paper.
Certain letters appear more often than speech than others.
Yeah, so we can try to be smart instead of trying 26 factorial combinations here. What we can do is to break this algorithm. By using statistical properties of the language. Of natural language. So in English, for example, we know that certain letters happen in the English language more often than other letters. So in English, the letter E occurs most often. Which is followed by T, O, A, and so on. So to break this, what we do is go and start counting the number of times each letter occurred in the text. And next we will order them by descending order, and whichever one is on the top, we replace it with E. Next one replace it with T. Next one replace it with O. After that, we can go to diagrams. For example, TH, IN, ER, this happens most often than that one and that. So after we start doing this with diagrams and trigrams, eventually the text starts making sense and it can be broken. Another cipher is called a transposition cipher. It's a little bit more advanced. So this transposition cipher will reorder the letters instead of trying to disguise them. So there's going to be a key, which is a word that should not have repeating letters in it. And what we do is write the message here. Please transfer $1 million to my Swiss bank account 6622. So we will write the message, and next, to transform this, we will take the column, the text which appears in the column number 1, that corresponds to the first letter of the alphabet, or A. So A is number 1, B is number 2, C is number 3. If we have D, it will be number 4. If we don't have D, we take the next closest letter, which is E, as number 4, and so on. So we will take the text in the first column, which is A, F, L, L, S, K, S, O, and write it here. A, F, L, L, S, K, S, O. Next, the second column. In the second column, we have S, E, L, A. So from here, S, E, L, A, W, A, I, A. W, A, I, A. And next, the third column. That's a little bit harder to guess, either by brute force attack or by statistical properties of language. Now, if we want to make it really difficult to exploit any statistical properties of the language, we can do some binary conversions. So we will take the message and convert it into binary. In this case, we are using ASCII encoding. ASCII is just the way we encode the keys on the keyboard for English. Every key has a 8-bit code. In this case, this is the code for I. I space. This says I love you, and then it has a period at the end. And then we can take that binary representation of the text and convert it from this plain text into a bit string. Then we pick up a random number called a pad and do an XOR with this pad. And once we do the XOR, the statistical properties of the language are gone, because any combination of letters is equally likely to happen. You can't have one being more likely than another. For example, if we take the same and apply a different pad to it, we will get, so first it was I love you. With pad 1 applied to it. If we apply pad 2, we will get this. Elvis leaves. So by doing this XOR, we are pretty much removing the statistical properties of the language. So in the second half of the class, we will see these were symmetric keys. In the second half, we will see the public and private keys.